Hello and welcome to the channel for the second part of chemical kinetics topic. In this video, today we are going to discuss about rate law and rate constant. Rate law is also commonly called rate law expression or rate expression. So students have a lot of confusion in these topics, and let's see them in detail today in this video. Stay tuned till the end and do not forget to subscribe this series for the entire topic of chemical kinetics for all national and international curriculums like IB, IGCSE, AP, EdXL, A levels, and all other curriculums, including the entrance exams, guys. Alright, so very quickly, let's check out the topics for today. Today's video, we are going to discuss the following learning objectives on your screen. Number one, the rate and molar stoichiometry. So how is rate related to the moles? Number two, the rate constant, also referred as K in the equations. Number three, the experimental concept, like the entire calculation is based on experiments. And finally, we will talk about the rate expression or the rate law expressions. So what exactly a rate expression is and how rate constants are a part of these expressions. Also guys, we will touch a bit about order of the reactions in this video, but we will just do the introductory part of the order. We will detail the order of the reaction in the next video, part 3. Alright, so very quickly, let's continue the video today with our first learning objective, which is rate and molar stoichiometry. Also, we can say as rate and concentration of reactant. So, let's take an example, guys. If you see this reaction on the screen now, this is PH3 phosphine. When reacts with HCl, hydrochloric acid, we get phosphonium chloride. So this is a simple reaction addition category. The two substances combine together to form one substance. Also, one important point to note is phosphine is a very important chemical which is used as a smoke screen creator. You know, the smoke screens that are created, generally it is done in military, and phosphine is one of the important chemicals used for that. Alright guys, and we have today's interesting fact about chemistry, guys. So the interesting fact is here, J is the only English alphabet which is not present in the entire periodic table. All other English alphabets are present in the periodic table. So every video I'm going to give you one interesting fact on chemistry like this, and do let me know in the comments section if you want a specific topic to be discussed. We'll try to bring a video on that. Alright, very quickly, let's come back to the point. We're going to talk about how in this PH3 plus HCl reaction, what happens to the concentration or molarity of HCl, which is one of the reactants, as the reaction proceeds. So you can clearly see in this graph, guys, as the reaction proceeds, in the beginning the molarity of HCl is 5 molar, but as the reaction continues, the reactant decreases, we all know, and we see a decrease in the molarity of HCl with time. And eventually, if you see at time 70.3 seconds and also at time 83.4 seconds, the molarity completely becomes 0. So what does this indicate? This is generally asked in exam questions, guys, that when does the reaction stop? So remember, when the change in concentration stops happening, we say that the reaction has stopped. So in this case, the change in molarity has stopped at 70.3. 70.3 we got a reading 0, and at 83.4 seconds another reading was also 0. So this means that entire HCl is used up and the reaction stopped. So this type of questions can be asked. Now you all know whatever happens in our world happens in chemistry, guys. So what is the real life or real world analogy for this decreasing the concentration or also decreasing the rate? As the reaction proceeds, guys, we will see in our further slides, as the reaction proceeds, the rate generally decreases. Now why like that? In the beginning the rate is fast, but as we go further the rate decreases. So I always give this real life analogy and example to my students. Whenever you are eating your favorite food or a snack or an ice cream, in the beginning, the rate of you eating it is very fast. So the beginning few chunks are very quickly eaten. But as you progress in eating and after few bites, guys, the rate of you eating that particular food slowly stops. Now the reason here is different, the reason in chemistry is different. The reason here is you become saturated, as in when you eat, and the saturation brings that feeling in the brain that okay, it's good, we have the blood sugar levels and all, and that's why the eating becomes slowest towards the end. The last few bites are very slow. Similarly, in a reaction, guys, if you see in the example we took in the previous slide, I have tried to bring a graph with molarity of the reaction, with the rate of the reaction with time. So when rate of this reaction with time was calculated, how can we calculate it? You know now, instantaneous rate, we discussed this in our part 1, is calculated by the change in concentration at that instant over time. So to plot the instantaneous rate, guys, we can draw a tangent on the concentration time graph, like how we have shown here. You can see there are 3 different instantaneous rates taken: R1, the blue tangent, R2, the yellow one, and R3, the red one. Now, if you notice clearly, guys, the tangent R1 is the steepest of all. And if you see here, that is somewhere around 7 seconds. So R1 is the rate of the reaction at around 7 seconds of time. Similarly, if you see, R2 is plotted somewhere around 17 seconds and R3 is plotted around 37 seconds. Now if you compare these 3 guys, R1 is the steepest, then R2 becomes less steep and R3 becomes much less steeper. I mean, the rate decreases. So rate R1 is greater than R2 and rate R2 is greater than R3. So as the reaction proceeds and the concentration of the reactant drops, the rate also decreases. But does this happen always? Or does it apply to all type of reactions? So let's go into detail in our next slide. So now we're going to talk about how in different scenarios the rate gets affected by concentration. When does it get affected and what is the effect like? So let's take the first example here in the next slide. If you see rate expression, we are going to introduce now. So what exactly is rate expression and how it is related to the order? Let's understand this now. So let's take the example of 3 different reactions, guys. Now for the first order, for the first type, first order, you take it as first type now, presuming that you have no idea about the order. Order we will detail in the next video, part 3. But first type is first order. Now if in this first reaction, the reaction 1 is 2 moles of X gives 1 mole of Y. Now in this reaction, guys, if you notice, an experimental graph is plotted. Now this is very important. This graph which is plotted is between rate and concentration of the reactant X. So concentration of product has no relation here in the current topic what we are discussing. So whenever someone says rate expression to you, rate expression will always be related to rate and reactant. It will never have product, guys. Just like, take an example in real life. When you're doing a journey from point A to point B, your speed is not dependent on the location of point B. Point B is the destination. So someone can go to the destination fast and some other person at the same distance can go to the location slow. So it completely depends on that person's journey, the person's vehicle, what he is using, and it's independent of the location where you have to reach. So that's why products play no role in rate expressions. So the most important guys in the rate expressions are reactants. Now in this example here, if you see 2 moles of X is giving Y, but when an experiment was done and the graph was plotted between rate and concentration, the result of the experiment was a straight line graph. So what does this mean? This means that the rate of this reaction is directly proportional to the concentration of X. Or if we remove the proportionality, we can say the rate of this reaction is equal to constant times x to the power 1, which is also x. So this constant which is introduced here, guys, is called K, and this K is the rate constant for this reaction. And then we can also go ahead and figure out the units of K. So before we go to the unit discussion, let's understand a few things. Number one, the rate of the reaction depends on the concentration of, generally depends on the concentration of one or more reactants. Point number one. Point number two, it does not depend in the manner of molar stoichiometry. Now you note here 2 moles of X are reacting, but we did not say rate is proportional to X to the power 2. We just said proportional to X power 1. Why? Because the graph is a straight line. How did we get the graph? By experiments. So that means rate dependency on the concentration is experimental. You cannot figure it out by the reaction balancing. Balancing can be anything, but the dependency may be different. Point number three, when you put a constant there and you remove the proportionality, that constant is called rate constant K, and the expression you get, guys, the final expression which you get is called rate law expression or rate law or rate expression of this reaction. So this particular reaction, in my example, the rate expression is rate is equals K square bracket, which is concentration of X to the power 1. This is the rate expression. So dependency is an experimental concept, rate constant is an experimental concept, and rate law or rate expression is also an experimental concept. These three have nothing to do with the balancing or the molar stoichiometric coefficient in the beginning of the reactant. Okay, so that 2 here does not affect any of these. Now very quickly, let's understand how we find the units. So to calculate the units of K, here we just bring X to the power 1 down the rate, and we get K is equals rate over concentration of X. You know, rates units we already discussed in the first video, part 1, is molarity per second, and concentration is molarity, capital M. So molarity per second over molarity, we get second inverse. So the unit of rate constant for the first order. Now why I'm calling it first order? Because my power of X here in the rate law is 1. Now what is order? How does this power affect everything? We will see in the next video. But for now, you remember one thing, that order is 1 if the rate is proportional to concentration to the power 1. Alright, let's go to the next example, guys. That was my first example. Example 2 or type 2 is 0 order. Now the name suggests 0. So let's see what's the difference. So we take another example here of a hypothetical reaction, reaction 2. 2y gives V. So in this case the reactant is Y. Now one experiment was performed and the graph was plotted for the dependence of rate on concentration. And surprisingly, the graph was straight line, parallel to x-axis. What does that mean, guys? That means in this particular reaction, the rate does not depend on the concentration of Y. Even if Y decreases during the reaction, the rate will not decrease. So then we do not have proportionality here. We just say rate is equals K Y to the power 0. Why Y to the power 0? Because there is 0 dependence. It does not depend. And that means it's a 0 order reaction. And here K is the rate constant again. But what is its value now? So its value is same as the value of rate. So rate is equals rate constant only for what type of reactions? For 0 dependency or 0 order reactions. So then what will be the unit for K? The same as units for rate, which is molarity per second. So again, remember one thing, this was found experimentally. If you see the reaction here, it says 2y gives V. But that does not mean the rate depends on y or its power of 2. It's not depending on it, guys. So again, it is not related to the molarity. It's not related to the stoichiometry. The dependency of rate on concentration is not dependent on the balancing of the reaction. It's totally experimental and can only be found out by experiments, like how this graph was made by an experiment. Alright, so we discussed about the rate expression and the rate constant for first order. Just now we discussed the rate expression and rate constant for zero order. Let's see what is I will give you the examples, guys. What are the reactions that follow first order? What are the reactions that follow second or zero order in the next video? In the next video, I'm going to detail what is order of the reaction. What are the various orders? What are the various examples of real life reactions that have those particular orders? But this video is not about the orders. We are just bringing in order to understand rate constant and rate expressions here. Alright, so now the third type of rate expression is of a second order reaction, guys. As the name suggests, now you must be getting an idea that in this reaction, the rate is going to depend on second power of the reactant concentration. So R is proportional to Z to the power 2. This was found out experimentally. Again, it has nothing to do with the balancing. As you can check, the balancing says 3 moles of Z gives X. So that 3 is not affecting it. It's depending on second power. So then if we remove the proportionality, we get rate is equals K Z to the power 2. So this is the rate expression for this reaction, guys. And here K is a constant called rate constant. And if we are going to find out the units for K, we'll keep K on one side. We will shift the Z square down to the rate and we will get molarity per second over molarity square, or concentration per second over concentration square. So 1m on the top and 1m at the bottom gets cancelled. So on the top we have 1 and down we have a molarity and a second. So we'll bring them up. So we will get the unit molarity inverse, second inverse. So that's the unit for rate constant for second order reaction. So let's do some exam style questions, guys. And this is a test your knowledge based on the 3 reactions I gave in my video. Try doing this question, and if you want the answers for this, and if you want to practice more questions, or if you want the PowerPoint which I shared here in this video, log on to my test shop and you can download this PowerPoint resource. If you are a new or aspiring chemistry teacher, do benefit from this resource by using it for your lesson. Also, if you want a worksheet for more exam style questions on this topic, below is the link for my test to download the chemical kinetics worksheet. Alright, so in the next video, I'm going to bring to you the different orders of reactions, their examples, and exam style questions on these orders. Stay tuned, guys, and do like this video if you learned something new today from this topic. Also, subscribe the channel and press the bell icon so that you keep getting the updates for the other videos of this topic. Goodbye for now.